Welcome back, everyone. Today we will be discussing the idea of the knowledge of the residual, which we talked about last session, which is the output of this residual generator. So our idea today is to have three important rules. The first rule is if there is no fault, if the fault is zero, then the residual should be as well zero. The second rule should be if the fault is not zero, then the residual R signal shouldn't be zero as well. Third is that in real life it is difficult to satisfy this condition is that if f is equals to 0, then r should be 0 as well. So third condition is if there are no faults, which means f equals to 0, then r should be approximately equals to 0. Today we will discuss the first idea of how to generate the residual signal r through the full order observer. So let's recap the idea of our plant, which was x dot of t equals ax of t plus bu of t plus ed times the disturbance signal plus ef times the faults, and y of t is equals to cx of t plus du of t plus fd of dt plus ff of f of t. So now let us design our observer. So the observer is as follows. The x hat dot of t, the estimated signal, should be equals to ax hat of t plus bu of t, and that's it. Why? Because these are the signals that we actually know. The disturbance and the faults, we don't know, so we can't estimate it. But what we can do is that we can introduce a new parameter, which is L times y hat of t, y of t minus y hat of t. Okay, whereas y hat of t equals cx hat of t plus du of t. Okay, here's our process model, and here's our observer. Now we want to design the L matrix so that the difference between x and x hat should equal to 0. So let us introduce a new parameter, which is the error, and let us denote it as x of t minus x hat of t, and let us substitute these two 1 and 2 here. So we'll substitute 1 and 2. First let us do E dot of t equals x dot of t minus x hat dot of t as well. So E dot of t equals to A x of t plus bu of t plus ed times disturbance plus ef times the fault minus x hat of t, which is this, which is minus a x hat of t minus bu of t minus l y of t minus y hat of t. This goes with that, and now we have E dot of t. First we want to substitute as well. Here's 3 and 4. Let us substitute 3 and 4 in 5. And knowing that, we tend to remove b of t with bu of t, this one. And knowing that x of t minus x hat of t equals e of t, we can simplify to e dot of t equals a e of t plus ed d of t plus ef f of t minus l, and y of t was cx of t plus du of t plus fd times dt plus f of t minus y hat, which was minus cx hat of t minus du of t. We can remove this with that, and yeah, now we can do a bit of simplifications. So e dot of t equals to, as you can see, ae of t, and we have here c x of t minus cx hat of t. This should be c e of t minus l, so it's minus lc times e of t, so we can augment it all in one place in a minus lc e of t. So we're done with this, we're done with that, we're done with this as well. Now what's left is the disturbance, what's subject in the disturbance and what's subject in the fault. So what's left is disturbance plus ed, so that's done with this one, minus lfd minus lfd times the disturbance. So we're done with this, we're done with that as well. So what's left is the what's subject in the fault signal, which is plus ef plus, I'm sorry, minus lf minus lf f times f of t. Now we want to design the L matrix so that E dot converges to 0. So we want to design A minus LC to be stable. be stable. Meaning, if it's in continuous in real time, so meaning that the eigen values should be in the left half plane, the left hand side. If it's in the discrete time, then the eigenvalues should be inside the unit circle. Okay. Now we know we designed L so that we have x of t and x hat of t similar. Now we want to actually design the residual signal, or here we can design it as w times y of t minus y hat of t. The residual signal actually can be only y of t minus y hat of t, but we can introduce this matrix for design purposes if we want to minimize the signal, increase its amplitude, and so on. But most of the time w can be just an identity matrix. So here, if the output is not exactly as the estimated output, then there is a fault. Then the residual is not equals to 0 anymore. And now we know that there is a fault. Let us see the dynamics of the residual by substituting y of t and y hat of t. So substituting 3, 3, and 4 in, let us say that's 7 for example. So substituting 3 and 4 in 7, we can have the residual signal to be w times y of t equals c x of t plus du of t plus ed d of t plus plus fd times d of t plus ff of t minus cx hat of t minus du of t. Now this can go with that, and the residual signal is equals to w c e of t, c e of t, since x minus x hat is the error, plus fd times d of t plus ff f of t. And that's the dynamics of the residual signal. As you can see, there is a huge problem in this design, which is fd times d of t. Now the residual, if the fault is actually 0, but there are disturbances, the residual would be not equal to 0. And this will be our topic in the next couple of videos, is how to actually decouple the disturbances from the residual signal, so that the residual signal is only affected by the fault itself.